Greetings, calculus students. This lesson is a second lesson in a four-part series on using derivatives to analyze the covariation between two variables. In other words, as x varies, how does y vary? In particular, this lesson is on using the second derivative to help with this analysis. Consider the image of the function below. A hypercritical number is an x-coordinate in the domain of f at which one of two things is true. Either the second derivative is equal to 0, or the second derivative fails to exist. So hypercritical numbers are to the second derivative as critical numbers are to the first derivative, as discussed in a previous lesson. Hypercritical numbers where the second derivative is 0 we will call type 1, and hypercritical numbers where the second derivative does not exist we will call type 2. Now a hypercritical point is a point x comma y, so both coordinates, where x is a hypercritical number. Now a function is said to be concave up on an interval if the slopes of the tangent lines are increasing on that interval, and concave down on an interval if the slopes of the tangent lines are decreasing on that interval. So looking at the image below, let's focus on this first portion. Imagine a point on the curve, and then imagine the tangent line. As the input variable increases, what is happening to the slope of the tangent line? I observed that the slopes of the orange lines was decreasing. They started at large and positive and then decreased. When x is -2, we have a flat spot in the graph, so the tangent line is horizontal with slope 0. Now you must be able to imagine these tangent lines. I'm going to use technology to help us with this imagination. So as x increases, I see the slopes of the tangent lines are decreasing, and by the time x gets to -2, the slope has become 0. Now as x varies from -2 to -1, we can see the slopes of the tangent lines increasing, becoming more and more positive until we get to this location where it appears that the slopes are as steep as they're going to get, at least for this portion of the graph. Now between -1 and 0, the slopes start to decrease, going back down to a slope of 0 when we get to this maximum point. Then we see the function decreasing, and the steepest point of descent appears to be right here where the slope is the most negative. So as x varies from 0 to x equals 2, we can see that the slopes are still decreasing. They're becoming more and more negative, which is a decrease. And then this is the point where the slopes are most negative, in other words, where they are the least. Backing up to this point here, between x equals -1 and x equals 2, the slopes decrease from positive to 0 to negative to more and more negative until we get to x equals 2 when the slopes are the most negative. So over that entire interval, the slopes were decreasing. Between this point, when x is 2, and this sharp corner, when x is 4, the slopes are now increasing because they're going from a large negative to less negative to less negative until we get to the sharp corner. Those are increases in slope. At the sharp corner, we have no tangent line possible. The first derivative will fail to exist here, and if ever the first derivative does not exist at a location, the second derivative will not exist at that location. This would be an obvious location of a type 2 hypercritical number as well as a type 2 critical number, because both the first and the second derivatives will fail to exist here. But now as x continues, along this linear path, the slopes of the tangent lines are not changing. And in this case, the slopes remain -1. So one more time all the way through. For this first interval, the slopes are decreasing from positive to less positive until we get to a slope of 0 at x equals -2. And now the slopes are increasing from 0 to more and more positive until we get to the most positive slope when x is -1. And then the slopes decrease from positive to 0 and continue to decrease to more and more negative until we get to the most negative at x equals 2. Between 2 and 4, the slopes are now increasing from large negative to less negative to near 0. At 4, there is no slope. And then as we increase, now the slopes remain a constant -1. So looking at our notes, I'm going to highlight in red all those portions of the graph where the graph was concave down, where the slopes were decreasing. I'll highlight in green all those portions of the graph where the slopes were increasing. And then in orange, all those portions of the graph where the slopes were not changing, which is this linear portion. So we can summarize, f is concave up, 4, x is in, and these are the green portions, and this is from x equals -2 to -1, union, and then between 2 and 4. F is concave down on the red portions, where the slopes of the tangent lines were decreasing, And we'll assume that the behavior of the function continues in both directions off of our viewing window. So we'll say the first interval is from negative infinity up to negative 2, and then union from negative 1 up to 2. And then for the orange portion, we don't say concave up or concave down. We simply say no concavity. And this would be for the orange portion where the graph is linear, which is from 4 to infinity. And the word concavity of a function simply refers to whether and where the function is concave up or concave down, or maybe has no concavity. Now the connection to second derivatives. If the second derivative of a function is positive on some open interval, then f will be concave up on that interval. If the second derivative is negative on an interval, then f is concave down on that interval. And if f double prime is 0 on an open interval, then f prime is constant, meaning the slopes of the tangent lines are constant, which means that f is linear on that interval. Think of that backwards. If you begin with a linear function, such as mx plus b, then the first derivative will be m, which is constant, and the second derivative will be 0. So these changes in concavity naturally break up our number line into 1, 2, 3, 4, 5 subintervals. And let's keep track of the sign of the second derivative. Wherever the graph is concave down, the second derivative will be negative. So that's the first and third subintervals. And the second derivative is positive where the graph is concave up, which would be the second and fourth subintervals. And the second derivative is 0 for any interval where the function is linear. Now, an inflection point is a hypercritical point around which the concavity changes signs. So, from this interval to this interval, the concavity went from concave down to concave up. We had a change in sign. So we have an inflection point, and I'll begin a list of all inflection points. One is at negative 2, 2. Then we had a change in concavity around x equals negative 1. So the point negative 1 comma 3 is another inflection point. Then a change in concavity around x equals 2. So this point, which appears to be around 2 comma 2.5, is another inflection point. Now around x equals 4, concavity went from positive to 0. This is not technically a change in sign. This will be a hypercritical point as well as a critical point, but for our purposes, we will not consider it an inflection point because concavity did not change sign. So we have only 3 inflection points. X equals 4 would be a type 2 hypercritical number because x equals 4 is in the domain. There is a point there, but the first derivative does not exist because of the sharp corner, and therefore the second derivative would not exist there either. Now negative 2, negative 1, and positive 2, these are certainly hypercritical numbers. It's harder to say from the visual whether they are type 1 or type 2. If I knew the equations that made this graph, then I would be able to make that determination, which we will do on subsequent pages in this lesson. But from the visual alone, it's not always easy to identify whether an inflection point is a location where the hypercritical number is type 1 or type 2. Every inflection point is also a hypercritical point by definition, but not every hypercritical point is an inflection point. For example, our blue point. So as we move forward, we are going to find hypercritical numbers and therefore hypercritical points, and then test the signs of the second derivative in the surrounding subintervals to determine whether there are changes in concavity to determine which hypercritical points are in fact inflection points. Okay, let's move on to the next page. Do a second derivative analysis of the given function. This means to find the following: all hypercritical points, intervals where the function is concave up, concave down, or linear, and all inflection points. Confirm by graphing with technology. Now this function is a 4th degree polynomial. I know that it will be smooth and continuous, no sharp corners, and no linear portions. We begin by finding its domain. Capital D for domain, sub f meaning the domain of the function f. This is a polynomial, and polynomials allow all inputs. So our domain is negative infinity to infinity. Now I want to get to the second derivative. Well, the first derivative, using the power rule, will be 4x cubed minus 12x squared, and then plus 0. And the second derivative, 12x squared minus 24x. Now at this point, I want to do a domain again of the second derivative. The second derivative is a second degree polynomial. Again, it allows all inputs. It's important to do the domain both of the original and the domain of the second derivative to look for any restrictions that might occur in that process. But in this case, there is no change in domain, so there are no type 2 hypercritical numbers. So now I just want to try to find the type 1 hypercritical numbers. We'll do that by factoring the second derivative. I can factor a 12 and an x out of both terms, leaving x minus 2. Now, if you were to set this equal to 0 and solve, you would get two answers, 0 and 2. These are your only type 1 hypercritical numbers. Now we make a number line that represents the domain of the original function, so all real numbers, the entire number line, and we put on it all hypercritical numbers. And there are only 2 of them, they're both type 1. Make sure they're in order. Next, we take test numbers from each subinterval, -1, +1, and 3. It doesn't matter which test number you pick from each subinterval. And then we plug these into the second derivative to see whether or not we get positive or negative. And normally I do this work in my head, and I use this factored version of the second derivative to just keep track of signs. So f double prime of -1 will be 12 times -1, which is -12, and then it's -3. But all that really mattered to me was that we had a negative number times another negative number, and a negative times a negative is positive. So the second derivative is positive on this interval. I like to put 2 plus signs to remind myself that this was a positive second derivative. That means we have concave up. Now let's test +1 into the second derivative. Using the factored form, I'd get 12 times -1. Again, all that matters is that it's a positive times a negative, which is a negative. So the second derivative is negative on this interval. I like to put 2 minus signs, and we say concave down. And now let's test 3. 3 times 12 is 36, and 3 minus 2 is +1. All that matters is that it's a positive times a positive. So the second derivative is positive. I'll put 2 plus signs and conclude concave up. So summarizing this, f is concave up for x is from -infinity up to x equals 0, union from 2 to infinity. And f is concave down for x is between 0 and 2. Now, around 0, we did have a change, and around 2, we did have a change in concavity. So we have inflection at both of these hypercritical numbers. So we have 2 hypercritical points, and both are inflection points. We just need to get the outputs. So let's plug 0 into the original function, which is here. Plug 0 in, we get 20 back. And let's plug 2 into the original function. 2 to the 4th is 16. 2 cubed is 8. Times 4 is 32, so minus 32. And then plus 20. 16 and 20 add to 36. Minus 32 gives me 4. So our 2 inflection points, which are also hypercritical points, are 0, 20, and 2, 4. Going to confirm by graphing, typing in the function and both points, changing my viewing window. I'll create a slider from -3 to 5, an orange point at capital T, comma f of capital T, and then the tangent line. Y equals f prime of capital T times x minus t plus f of t. And we can see, so initially the slopes are increasing until we get to a slope 0, and then they are decreasing until we get to a maximum steepness when x is 2, and then they increase back to 0 and continue to increase forever after that. Okay, let's go to the next page. Same instructions, new function. G is the cube root of x squared. That could be rewritten as x to the 2/3. The domain of G, well, you can square any number and then you can cube root any number, positive, negative, or 0. So there are no restrictions here. We have all real numbers as our domain. Now let's find the first derivative. Power rule, 2/3 x to the -1/3. And then second derivative, -1/3 times 2/3 is -2/9. And the power drops from -1/3 to -4/3. This could be rewritten as -2 over 9 times the negative power pushes the x to the denominator, and then the 4/3 power is the cube root of x to the 4th. But now that x is in a denominator, 0 is no longer allowed. So the domain of the second derivative, we must remove 0. -infinity to 0, union 0 to infinity. So comparing to the original domain, we lost x equals 0, which means x equals 0 is a type 2 hypercritical number. Now let's look for any type 1s. Set the second derivative equal to 0 and solve for x. Now if you have a fraction, a over b is equal to 0, that implies that the numerator must be 0. If I set the numerator equal to 0, this is an impossibility. There's no solution, so there's no type 1 hypercritical numbers. Okay, next we make our number line that represents the domain of G, so all real numbers. We put on it the only hypercritical number, which was 0, a type 2 hypercritical number. We pick a test number, so -1 and +1, and plug these into the second derivative. I'll plug into this version of our second derivative, plug in -1, we get -2 over 9 times the cube root of -1 to the 4th. Well, that -1 to the 4th will go to +1, and the cube root of +1 is +1. So in the end, we get -2/9. But the second derivative is negative, is what matters. So I'll put 2 minus signs and conclude concave down. Now let's plug +1 into the second derivative. We get -2 over 9 times the cube root of +1 to the 4th. This will also give me -2/9 in the end. So the second derivative is negative on this interval as well. Two minus signs, concave down. Notice no change in concavity, so we will not have an inflection point in this case. To summarize, g is concave up, never. G is concave down for x is in the interval from negative infinity to 0, union 0 to infinity. Let's go ahead and find the output when the input is 0. So g of 0, I'm looking at the original function now, is the cube root of 0 squared. That's just going to be 0 back. So we do have a hypercritical point at 0, 0, but it is not an inflection point because the concavity did not change. Confirming in Desmos, I'll keep my slider programming. In our notes, the function was g, but I'll call it f so that my programming here can remain intact. The function was x to the 2/3. Make a few adjustments. Here's a graph of our function. Reveal the tangent line again from -7 to 7. You can see that the slopes are decreasing, becoming more and more negative. And then after the hypercritical point, the slopes switch to positive, but are still decreasing as x increases. So both portions of this are concave down. Okay, next page. Same instructions, new function. H of x is a rational function. The domain is going to have a restriction because we cannot divide by 0, and if x is 1, we'll have division by 0. If you try to plug 1 into this function, you'll get 1 over 0, and non-zero over 0 in a rational function always indicates the presence of a vertical asymptote. But x can be anything from negative infinity to 1, union from 1 to infinity. Make a note to myself that there will be a vertical asymptote at x equals 1. Now we got to find the second derivative. But first we find the first derivative. I do see we have a quotient of two functions, so I will use the quotient rule, which will be u prime v minus uv prime over v squared. So we have the derivative of the numerator, which is 1, times the denominator, minus the numerator times the derivative of the denominator. And for that, we have to use the generalized power rule. So the 2 will drop down, the base stays the same, the new power is 1, which I won't write, and then we have to multiply by the derivative of the inside, which is a 1, which I don't need to write, all over the denominator squared, which will become x minus 1 to the 4th. Now do some factoring. There are two terms in the numerator, and both terms have one x minus 1 I could factor out, leaving left over a single x minus 1 minus a 2x, which in the end simplifies to x minus 2x in the red brackets becomes negative x, and then we have minus 1 all over, and we have cancellation of one of the factors of x minus 1, leaving a cube on the denominator. But now we got to find the second derivative. So I'm going to think of this as a new u over v, and again, use the quotient rule. So we do the derivative of negative x minus 1, which is negative 1, times the denominator. So just negative parentheses x minus 1 cubed, minus parentheses the numerator, times the derivative of the denominator. Using generalized power rule, we would have a 3x minus 1 new power 2, and chain rule would be times a 1, which I won't write. And then all over the denominator squared, which will lead to x minus 1. And when you square a cube, you get a 6th power. Now I'll do some similar factoring. I can factor out x minus 1 squared from both of these terms. So that will leave left over. We have a minus sign, one copy of x minus 1, minus, we have a 3, which I'll put, parentheses, negative x minus 1, and that is all that remains in the red brackets. Now this x minus 1 squared will cancel with this power 6, leaving a power 4. And then inside here, I'm going to do some distributing of these negatives and combining of terms. So we get negative x plus 1 plus 3x plus 3. All over x minus 1 to the 4th, which gives me 2x plus 4 all over x minus 1 to the 4th. Now we want to give the domain of the second derivative. But once again, 1 is the only restriction here because of that denominator. So our domain of the second derivative will be identical to the original domain. So there are no type 2 hypercritical numbers. But if you take the second derivative and set it equal to 0, which means that the numerator must be 0, and solve this for x, we get 2x must be negative 4, therefore x must be negative 2. This is our only type 1 hypercritical number. All right, now a number line that represents the domain of this function h, and there is a restriction. So we need to exclude x equals 1, and the reason is that there was a vertical asymptote at x equals 1, and then we also need to put the hypercritical point of negative 2 on this number line. Now, 3 test numbers. I'll go with negative 3, 0, and 2, and plug into the second derivative. And I'll do this work in my head. Let's plug negative 3 into this second derivative that's simplified here. Negative 3 times 2 is negative 6 plus 4 is negative. So a negative numerator, but negative 3 minus 1 is negative 4, but raised to the 4th. In fact, this 4th power is going to guarantee that the denominator is always positive. So we get a negative numerator over a positive denominator. That's a negative result. So the second derivative is negative. I'll put 2 minus signs and conclude concave down. I'll plug 0 into the second derivative. We get positive 4 over a positive denominator. The second derivative is positive. I'll put 2 plus signs, concave up. And plugging in 2, we'll get similar, a positive second derivative, so also concave up. H, concave up on the interval from -2 to 1, then union, and then from 1 to infinity. H, concave down on the interval from -infinity up to -2. There's only one hypercritical number, and the concavity does change sign, so we will have an inflection point. Be careful, we don't need to bother analyzing the change in concavity around the asymptote, because even if there was a change in concavity around the asymptote, 1 would not be an inflection point because 1 is not in the domain. So we have one hypercritical point. Also, it's an inflection point. It's at -2, comma, h of -2. Let's figure out what that y-coordinate is. -2, comma, and now I look to h, plug -2 in. We'll have -2 in the numerator. -2 minus 1 is -3. Square that is 9 in the denominator. So -2/9. Okay, let's confirm with technology. I type in the new function, typed in my hypercritical point. I typed in the vertical asymptote at x equals 1. I'll let my slider go from -7 to 7. Now, it is difficult to determine visually that the inflection point is right here. I would need to change my vertical scale to see this better. And then revealing my tangent line, we can see that the slopes are decreasing until we get to this inflection point, and then they turn around and start to increase, and then forever increase until the asymptote. And on the other side of the asymptote, the slopes are decreasing forever. All right, moving on to the next page. Same instructions, new function. This function is part polynomial, part exponential. There are no domain restrictions for either of these pieces. So the domain of capital F will be that x can be anything from -infinity to infinity. Capital F prime, I will need to use the product rule, which will give me u prime v plus uv prime. So in this case, the derivative of 2x is 2 times the exponential plus the 2x times the derivative of the exponential. We have to use the chain rule here. The derivative is itself times the derivative of -3x. So minus 3e to the -3x, giving me 2e to the -3x minus 6x e to the -3x. Do some factoring and factor a 2 and the exponential out of both terms. That leaves 1 in the first term and then minus 3x. Now I'm going to differentiate again using the product rule, but we have a new uv. So the derivative of 2e to the -3x will wind up being -6e to the -3x. That's using the chain rule, times the second plus the first times the derivative of v, which will just be -3. Now I'm going to do my factoring up front. Now there are two terms here. Let's see what's common to both terms. There will be a -6 in both terms that can be factored out, as well as the exponential in both terms that can be factored out. So we get -6e to the -3x, and then inside the red brackets, we would have in the first term only the 1 minus 3x, so I don't need to put it in parentheses any longer. And in the second term, everything was factored out, so there would be a plus 1 in its place. So in the end, our second derivative is -6e to the -3x times 2 minus 3x, and this is in factored form. We do its domain next. This function is still part exponential, part polynomial. There are no domain restrictions for either of those. So our domain is once again -infinity to infinity, and we compare to the original, there is no change. So there are no type 2 hypercritical numbers. So when I set the second derivative equal to 0, and because it's factored, either this factor must be 0 or this factor must be 0. In this first case, you could divide the -6 away, because 0 divided by -6 is still 0, but this is no solution. Keep in mind that e to a number must always be positive. E to a number can never be 0. However, the second equation, we do get an answer. 2 must be equal to 3x, so x must be 2/3. And this is our only type 1 hypercritical number. Next comes our number line that represents the domain of the function f, so the entire number line is here. We have only one hypercritical number, that's at 2/3. So some easy test numbers to choose would be 0 and 1. Now f double prime of 0, I will be plugging into this factored version of f double prime and keeping track of the signs. We would get -6e to the 0 times 2 minus 0, or just 2, but e to the 0 is 1. So we have a -6 times a positive 1 times a positive 2. And negative times positive is negative. So capital F double prime is negative on this interval. I'll put 2 minus signs is another way to indicate that. And we have concave down. Now f double prime of 1 will be -6 e to the -3 times -1. The e to the -3 is not a negative number. It just means 1 over e cubed. With that realization, I can see I have a negative times a positive times a negative. That's a positive overall. So I'll put 2 plus signs and conclude concave up. Summarizing, f is concave up on the interval from 2/3 to infinity. F is concave down from negative infinity up to 2/3. We do have a change in concavity, so our hypercritical point will be an inflection point. We'll be at 2/3, comma, capital F of 2/3. So I look at my original function and plug in 2/3 for x. 2 times 2/3 is 4/3. Negative 3 times 2/3 is negative 2, which we could write this point as 2/3, comma, 4 over 3e squared. And this is our inflection point. Let's confirm with technology. I changed the function, plugged in our point, zoomed in a bit. Let me change my y scale as well, making it slightly easier to see that we have inflection at this hypercritical point. We can see that the slopes of the tangent lines are decreasing until we get to the inflection, and then the slopes are increasing, approaching 0 as we follow a horizontal asymptote. So concave down until the inflection point, and then switching to concave up. Now moving on to the last page. The second derivative can sometimes be used to determine whether a critical point with f prime equaling 0 is a local extremum, which means a local max or a local min. This is known as the second derivative test for identifying local extrema. Now the concept here is actually rather simple. Let's say a function has a flat spot that is a local max. Imagine the tangent lines as you move through this critical point. The tangent lines would be in a state of decreasing. In other words, what we're seeing here is a concave down portion of a curve. So if you have a flat spot on a curve and the second derivative is negative, meaning concave down, this would imply that there's a local max. Thus, suppose we have x equals a is a critical number with f prime of a equaling 0. So this is a type 1 critical number, a flat spot in the graph. If the second derivative at this value is negative, then there is a local max at this point. What if you have a function with a min where the derivative is 0, so type 1 critical number? Well, here, as you transition through this extremum, the slopes would be in a state of increasing. So we would have a concave up portion of the graph. So if the second derivative is positive at this location, then there will be a local minimum at this point. If the second derivative at the critical number is also 0, then the test is inconclusive. I'll illustrate this after we do our example. Use the second derivative test to determine which critical points of the function below are local extrema. Confirm with technology. Okay, we have a 5th degree polynomial. The domain of this polynomial is all numbers. Let's find the critical numbers. Now, not hypercritical numbers, so I just need to do the first derivative and pause. The first derivative, the 5 times 1/5 goes to 1, power drops to a 4, minus 4/3 times 3 is 4, power drops to a 2, and we are done. The domain of the first derivative is also all real numbers, so there's no type 2 critical numbers, but I didn't want those anyway. I only want the type 1 critical numbers. So we factor the derivative, first factor an x squared out. Now we have x squared minus 4, that's a difference of squares, so that can continue to factor into x minus 2 times x plus 2. So if I set the first derivative equal to 0 and solve, I'm going to get 3 answers, 0, 2, and negative 2. These are all type 1 critical numbers. They are the locations where the graph will be flat. Now the second derivative test says find the second derivative, and I'll begin with this first derivative to find my second derivative. Power rule, we get 4x cubed minus 8x. Now all I do is I plug these type 1 critical numbers into the second derivative and see whether I get a positive or a negative, or maybe 0. And we can make a little table. So we'll pick a type 1 critical number, plug it into the second derivative, and then give our conclusion based on the second derivative test. I'll go in order. The least was negative 2. Plug negative 2 into this second derivative. Negative 2 cubed is negative 8 times 4 is negative 32. And to that we'll add 16. So we get negative 16. So we have a flat spot in the graph when x is negative 2, and the concavity is down because the second derivative is negative. That puts in my mind this scenario, which means that we would have a max, a local max, at x equals negative 2. The next is 0. Plug 0 into the second derivative, we get 0 back. This is inconclusive as far as this test is concerned. And now let's plug in the largest critical number 2. 2 cubed is 8 times 4 is 32 minus 16 will give us positive 16. So we have a flat spot in the graph where the second derivative is positive, so that means concave up. That should put into our mind this image, which leads to the conclusion that we have a relative or a local min at x equals 2. And this would be as far as the second derivative test can take me. If I want to know what's going on at 0, because this test was inconclusive, we would need to do a number line monotonicity test. So I would do a number line with the domain of f on it, the entire number line. I'd put all of my critical numbers, pick some test numbers, and plug them into the first derivative, not the second, because I'm trying to determine monotonicity, not concavity. Using the factored form of the first derivative is advantageous here. Plug in -3. -3 squared is positive. -3 minus 2 is negative. -3 plus 2 is also negative. So the first derivative, this is a positive result, which means the function is increasing. Plug -1 into the first derivative. I'll get a positive, negative, positive, which is a negative result, meaning the function is decreasing. Plug in +1, I'll get a positive, negative, positive. So still negative, function still decreasing. And then plug in a 3, we'll get positive, positive, positive. So positive first derivative, increasing. And keep in mind that these are all signs of f prime, not f double prime. Well, this confirms what the second derivative test gave me. We had a change in monotonicity here in such a way that we have a relative or local max. And here we had decreasing to increasing, suggesting the location of a relative min. And because around 0, we had decreasing, flat, and then more decreasing, this was a flat spot, but not an extremum, meaning not a max nor a min. Be careful you don't assume that just because the second derivative test is inconclusive, that means there will not be a local max or min. Let me give you a quick example. Suppose our original function was x to the 4th. This graph looks something like this. It does have a minimum at 0, 0, but the first derivative is 4x cubed. Plugging in 0 into the derivative gives you 0 back, so we have a flat spot. So 0 is a critical number, but the second derivative is 12x squared, and when you plug 0 into this, you get 0 back. So the second derivative test is inconclusive, but this is clearly a case where we have a minimum. And then just looking at this function with technology, Desmos does identify for us all of these critical points, confirming our work that we have a local max when x is -2, a flat spot that is not an extremum at x equals 0, and then a local min at x equals 2. Okay, this concludes our lesson on the second derivative analysis, which is how the second derivative can be useful in helping us describe the properties of a graph.